Okay, everybody, my name is Aaron Wallace. I'm a master's student at Virginia Tech, and this is part of my final project. I'm using SPARTA DSMC to perform some simulations. This is the last video that I'm going to be producing. The previous three videos, we had two videos, the first two that were 1D problems from uh, chapter 12 of Bird's textbook, and then we had the last problem came from a journal article, and it was a flat plate in a supersonic flow. This is the next problem that came, or the next benchmark case that came out of that journal. And it is an interplanetary probe that's, I guess, they're trying to replicate it entering the atmosphere, and then they're comparing it to some wind tunnel testing that was done in the past. So we'll step through it. I found, I did have some issues running this. I can run it and get some reasonable results, but I have a couple of issues where I'm not sure what they did in their simulations. The info is kind of sparse inside of their journal article. But right here you can see in this table 6 that I'm showing you right now, this is from my report. It shows the parameters that were given inside of the journal article. And so that's what I kind of based my simulation off of. And then they talked about, one of the things they said was that they used about 20 million particles for this simulation. And they gave me the N row and the F num, and like I started with that, and then I ended up not having nearly the particles that I was supposed to have. So we'll discuss that a little bit more when we get to that part of the input script, and we'll talk about what I did. And let me just walk you through the scripts first of all, and then I'll show you the results I have currently. This simulation is at the limit of what my laptop can do. It's this simulation with the input scripts I'm showing you now takes me about 2 days to run, and this is only, I guess, probably about 40% of the particles or 30% of the particles that they said they had in their simulation. So I have one running with the 20 million particles right now. It's been running for like 4 days, and I'm not sure when it's going to be done. But anyway, let's discuss it, and like you can get some reasonable results in about a day's worth of time, but it's not it's not as detailed as you would like. So let's start. First of all, when we're going through here, we have to have the surface that's going to go into our box, because we're going to be actually doing this as a 2D AXISYMMETRIC problem. So we have to draw out the surface. And so I went ahead and downloaded FreeCAD for Linux and did my probe in that. And so, like, you got to draw it up. And remember from I guess it was the last video, we discussed some on how you have to define the surface inside of SPARTA, and it's got to be done in 2 dimensions with points and lines. So whenever you're doing it with points and lines, you actually have to have points that it goes from. So that was one of the challenges, is how do I draw this thing, and then how do I get actual, like, XY coordinates around all these curves that are, like, you can see there's curves here in the bow, and then there's a curve up here on the, I guess, like, kind of the edge of it. And I just drew, it's axisymmetric, so I drew one half of it, and then we imagine that this rotates all the way around to make, kind of like a mushroom shape. This is the first time I've dealt with this shape, but I'm imagining in aerospace it's not very uncommon. So I sketched it all out. I downloaded FreeCAD for Linux, and it took me a couple hours to like figure out how to use it, and watched a couple YouTube videos about how to dimension things and lock everything in place. That wasn't too bad. Got that, and then I had to figure out, well, how do I get these data points all around here? Because when I enter my Sparta file, I have to basically describe points all the way around this surface, and then connect it with lines. And so what I did was I got Claude AI to help me write a macro for this for FreeCAD, and it's pretty interesting. Once you write the macro, let me see if I can open it up here. macros. So you can see it's just this, and it tells me in my curve segment I want to sample it 200 times in every curve. In a line segment, I'm going to sample it 250 times. And then it's just, and Claude helped me create this. It's something I could do, but how much time would that take you to do? And then once you've created it, you have it. And so we'll go back to the sketch here. And then I believe if I just run the macro, and then view, I forgot exactly where you pull it up to look at it. It's been a week or so, but you can pull it up and it's right down here at the bottom. It just gives you a list of XY coordinates for every point that you did along that surface, and it like breaks it up in curve and line. So it'll start at 0.1, and I've got it super fine right now. The simulation I'm going to show you, I didn't have it this fine. And so that's what I did with that. You just got to like kind of fight your way through it, figure out a way that you want to capture what these X and Y coordinates are, because that's how you have to lay it out inside of your SPARTA file. And I'll use this one for example, because this is the one that I'm going to use in this input script here. This is fine. I just called it fine because when I started out, the first instance when I did this, I only did like 100 points and 100 lines, and the sample points were not really where I wanted them to be to match up to the results that were in the journal data. So I discretized the lines more so I could have a place that will be closer to my data points. And you can see when I go over here to the fine one, I have 350 or 380. And I only did it for the front and all the way down the top, I guess, or, but the very back of the thing of the probe, I made one line. And then the part that sits on the AXISYMMETRIC axis, the x-axis, I just made that one line too, because we're not taking any data from there because this thing is revolving all the way around. Okay, so that shows you how I did that. And the whole structure of the SPARTA file, surface file we talked about in the last video. And again, you just got to, declare how many points, how many lines, and then you got to have an index number for every point, and then the XY coordinates. All right, so next, this is my species file, and I just got this out of the SPARTA example data or whatnot. It's the species file. It gives all the species information for everything that would be in air, and we're going to be using just N2 for this simulation. And so when I call it out inside of the input script, I only call out N2, so it's only going to pull in the information for N2. The same thing with our collision file. It's got all this, came straight out of the SPARTA data, and it's got all the information for everything that's going to be inside of air. I made a note down here that if you do have a mixture, like this simulation is going to be done with just N2, but if you do have a mixture, you will have to add info on the cross collisions of the species, like we did in example 2, where we looked at the mixture of argon and helium and did that. So, if we had O2 and N2 in here, we would also have to have the O2 N2 collision parameters. And they're given in the back of Bird's book in Appendix A, I believe. All right, so this is just where I helped use, this is just nothing important. It comes from one of the examples, and it's something that I used to help me see the structure of how they did it. So then we'll get into our actual input file. And this is where you start getting into some of the details. And I laid out the box the way that I seen that the way they did it inside of the journal article. And I'll add a link to the journal article, or at least I'll add the information that's needed to find the journal article into the text of the video here. So I created the box the way we talked about doing it. And here are my boundaries. The difference here is we're saying that the Y boundary is axisymmetric and then reflective. And so that just means that we're going to rotate around it in an axisymmetric, and then the top end is going to be reflective. And this is the way it seems that they did it in their article, and I tried to mimic everything I could. It's got the same grid size, 800 in the y direction, 800. I mean, in the axial. I'll start calling it axial and radial if I can, but 800 in the axial direction, and then 800 in the radial direction, and then one, of course, in the z direction, because you always are having to define that other dimension. All right, and then I use the same rebalancing that they used inside of the article, and this just helps if if your processors get out of balance when they're running. I don't know if this helps me at all here running on my laptop. I'm really starting to learn that this is something that most people run on big clusters inside of their school or inside of their research laboratory. All right, so next we get down to the gas and species mixture. We're going to call from that file air.species into. That means we're pulling the information from into. And then for our mixture, we got air, and then we just have the into. We're setting the initial velocity, or the B stream velocity. So it's B infinity is going to be 1463.27. That's what they had. Temperature at infinity is 13.32 Kelvin. That's what they had in their journal article. And then in row is 3.869 e to the 20. That's what they had. So all this data came directly from his journal article, their journal article. All right, so then we look down at the particle weighting, and this is one of the really odd things about this, where I'm still I'm not sure what they did. So when I first started out, I looked at the AXISYMMETRIC examples that they have inside of the SPARTA download, and they used it. They used radius as how they did the particle weighting. And when I say particle weighting, it means I think it's how they how they populate the particles inside of the grid. And so I started with the weighting by cell, and then radial or radius, and I ran it with the proper FNUM, which is, let me pull this back up. FNUM should be 7.2 e to the 16. All right, you can see here I have 3.6 e to the 16, so that's half of what they had in the journal article. So when I ran it with the 7.2 or whatever they declared in the journal article, I actually only got 3 million particles. And I ran the simulation, and it gave me some results. Like near the front of the probe, I could get reasonable results that were within 10% of what they got. But I was like, so I started playing around and trying to see. There's another way to weight the cells, and you can weight the cells by volume. And when I weighted the cells by volume with the proper FNUM that was given in the journal article, I ended up at 63 million. And so it didn't even it was running so slow, I think it would take over a month to complete. And so what I decided to do was stay with the weighted cell radius, and then incrementally increase the number of particles by decreasing FNUM. And so this is the first time that this script here is the first time I've done it. And so I just divided 7.2 e to the 16 by 2, and then changed my FNUM to that. And that's where I get my 3.6 e to the 16. And then when I did this, I ended up getting about 7 million particles, or between 6 and 7 million. And the results were actually a little better. So I've done that twice more, and the one I have running now has 21 million particles in it, and it's been going for over 2 days, and it's only maybe a quarter of the way there. So I'm just letting it run, and then when it's all said and done, I'll look at it. But this is something I'm still not clear on how they did it in their article. But this is the way I'm doing it: is I'm weighting the cells by radius, and I'm decreasing the FNUM. That way we get more simulation particles, and trying to get close to what they had inside of their simulation. Next we put the gas collision model in there. That's the same thing that we've done before. It's you call VSS. I'm saying I'm going to use what's called air, which air is going to be my N2 because I called it air here in the mixture. And then I'm just saying I'm using this collision file air.vss to get my information from. All right. Um, next thing we did, we had our I just fixed here. This is, like I said, I think it's, I've seen it in the other one, in the other examples. I think it's how they lay it in there. I need to do some more research on what that fix actually does. All right, next we read in our surface geometry here. You see I read in the surface as data probe find. That's the one we looked at a minute ago. The origin is at 0, 0. So I tried to set everything the way they did inside of their journal article. I used diffusive collisions. It said that the wall temperature of the probe, I guess the probe temperature is 300, and then all of it is diffusive by this 1.0. Then I just surf modified all collide 1, so that means all my collisions are going to be based upon this, information. All right, next, this is the same grid property computation that I did in the previous example. So if you got some questions, go back and look at that. I don't really think it's needed to go back over it all again. Next, we got the statistical output. That's the same as it was. When I was doing it on the volume weighting, I actually changed this to 1 so I could see if it actually was moving. It would move up. It would do one time step about every 15 to 20 seconds. And since there's 120,000 time steps that have to happen, that's pretty deep. And it would actually increase as it would populate because you get more and more. Like it was still building up to the full number of particles for steady state. All right. The global time step is 1.3 e to the 7. That's what they used in the journal article. They said they ran it 100,000 time steps, and then they took data. I think they said they may have took 10,000 time steps of data. I'm just taking 20,000 just to try to smooth things out a little bit. We used the same process for all this that we did before, so nothing's really changed there. In that part. And so come back in here and let's look if we're going to run it, we'll just open it in the terminal, and then you see this is how I would run it, and then we'll show that it runs, and it still moves pretty slow compared to the previous examples, but it is moving, and it takes probably about 20,000, no, I don't know, about 3,000 or 4,000 time steps for the particles to kind of level out to where they're going to be. And you can see here's the one I've got running that's got right at 20 million particles, and it's been running over 3 days or 2 days, and it's only got 28,000 particles. This is one I started similar to this, I think, yesterday, and it's almost done. I'm just trying it one time with the variable hard sphere model just to see what I get from that. He didn't say, or they didn't say in their journal article, whether they used variable hard sphere or variable soft sphere collisions. So I went with the variable soft sphere, but now I'm checking to see if maybe I get better results with the variable hard sphere. And I've got my results in here, and you can see instead of running, I did create another program on with Python to do all the post processing and all. And I've started building my my project reports. I can just show you from here. This is the heat transfer, and you can see up here at the front, it's like 10 kilowatts of heat flux per meter squared, and it's reasonable. Like I'm pretty close. You can see mine is the blue, and then the experimental values are the stars, and the green is the author simulation, and then and when for the experimental values in this area, it just said that it's less than 0.002. So like these numbers um, are actually fine. That's not an issue. Up in here, you can see I've deviated from it some, but it's reasonable. Like, and then right here, I think I'm only working with like 7,000. I think this is the data from the 7 million particles. So like it's reasonable. You can get something. The heat flux in the front is way greater than the heat flux everywhere else. So if you were going to really be looking at it, this is where you would be looking on your probe anyway. And I believe that the journal article actually talked about how they use thermocouples on this probe in the wind tunnel testing, and they were saying that it's probably not accurate like it is up in the front of the probe because of the variations that were going on in the, I guess, downstream end. All right, so here we can see I got a table here with my data that shows the difference. And what I did was in my Python program, I built it to go through and look at the closest points on my in my data from my surface file and find out which points were closest to the points of evaluation, which these are the points that they gave in the journal article that were based on the thermocouple positions. And so this just shows, like, with it being broken up fine like I have it, I'm able to get this close to what they said. And this is also this is S divided by Rn, and so it's got something to do with the radius and, I mean, the length down the surface, and the radius of the nose of the probe. And the journal article had, I don't know, the sketch that they had in there, it was missing some information, I feel like, to get like a complete picture of everything you needed to sketch it out. So like, I wouldn't doubt that I'm slightly different in my sketch than they were. And when I say slightly, I mean very slightly. All right, so you can see like my values here versus the experimental values, and here's the journal values here. Um, and so you see like it's tracking really well. It's not bad up in this front, and but when it gets back towards the back, it starts to have some issues. And like you can see, the journal article has some issues back here, even though they're not as great as mine. He's able to um, really pin it down in the front of the thing. I think it's because of the amount of particles. And you can see this is the total velocity. On the left comes from the journal article. On the right comes from my SPARTA simulation. And they're really close with the total velocity, with the x velocity and with the y velocity down here. You see slight negative places in here, as you would expect from the vortices that are going to form in here. I'm a little off of what he has, but yeah, it's reasonably close. The rotational temperature, reasonably close again. So that's a good sign. You can see like the shape, everything seems to be, it's the program's working. I think we got problems with the number density because we don't have the proper amount of particles. So next we look at the total temperature. I think there's an issue here with the way on the left is their image from the journal article, and we talked about how the free stream temperature was like 13.2 Kelvin. So I set mine up to show that, and it definitely shows it, which is what you would expect. You would expect it to be outside of the shock wave, which would be coming right here where you have these temperature change. You would expect that to be the free stream temperature. And in here, I think maybe they just picked a poor background color, so that might be part of the problem. And so that's how that's working. Let's see. So we get down talking about the number density, and you see his number density is still, his maximum is much greater than mine. I mean, it's not double, but it's a third more. And but you can see the number density is, like, as you would expect, it's piling up at the front of the probe. So like it's hitting, it's as it's going through there, it's packing up into here, and that would be what you would expect. All right, so I think that covers it. I'm gonna put these files into a GitHub repository. I'll try to put that add that to these videos because I've created a repository for everything. So I'll try to add something to these videos that I've posted and this video, and then that way you can pull it up and you can run it yourself and see if you can figure out maybe what I've done wrong or maybe what I could have done better. If you see something, I'm still trying to learn this, and I hope to be able to do some more of this. Unfortunately, my work doesn't involve this for my full-time job, but who knows? Maybe one day it will. But anyway, this will probably be my last video for this project. I want to thank Dr. Chow and Dr. Gonzalez at Virginia Tech University for helping me out with this project, and of course for SPARTA and the people that I guess invented it or developed it at Sandia Laboratory, and it's all open source, and it's actually like it's a challenge, but it's actually really cool, and I think you can do some really fun things with it. There is a limit to what you can do just based upon your computer. I got a pretty high-end laptop, and it's at its point here that this is the max it can do. One thing, I am using a virtual box, so I think that could be something that's kind of slowing it down because it's not able to really access the processors without running through another system. And so I hope next thing I want to do is I'm going to get me a computer about the same quality as this, or get a desktop computer, maybe gaming style, and then try to just load it with straight Linux and try running some of these things again and see how it does. But anyway, feel free to comment, and if you got any pointers, let me know. And like I said again, my name is Aaron Wallace. I'm a graduate student at Virginia Tech. This is my final project, and thanks for watching. Hope you take care. Bye.